Second thing we're going to look at today is empirical formula, which is almost the exact opposite of percent composition. In percent composition problems, we started with a formula and ended with a percent by mass. Here we start out with mass quantity, then we end up with a formula of some kind. This is what the empirical formula is. It's defined as the ratio of one element to another in the smallest whole number form. For an ionic compound, you find the empirical formula, you know the formula of the compound, you've identified it. For a molecular compound, something that's made all of nonmetals, the molecular formula's subscripts might be the same as the empirical formulas, but they might not. But at least they will be whole number multiples of the empirical formula's subscripts. So for example, CH2 is the empirical formula for CH2, but it's also the empirical formula for C2H4, C3H6, C4H8, or any compound that has twice as much hydrogen as carbon. Once we can find the empirical formula of a compound, we're well on the way to identifying what an unknown compound is. And so this is a valuable technique that real-life chemists use. You make something in the lab, you want to know what it is. Determining the empirical formula from the mass data gets you part of the way to being able to fully understand what compound you're dealing with. An empirical formula is really just a ratio of atoms that are in the compound, or moles. So for example, say we had HNO3 as a compound. This is what that formula really means. It means for every 1 hydrogen mole, there are 3 oxygen moles. And for every 1 hydrogen mole, there is 1 nitrogen mole. The subscripts give us these ratios: 1 to 3, 1 to 1. So that's our objective. We want to find out what those ratios are so we can turn them into subscripts in a formula. So here are the steps. To find empirical formula from mass data, if you're given mass or if you got mass from the lab, the first thing you want to do is change the mass into moles. And you can do that using molar mass. We're familiar with how to do that. The second thing to do is, once you find the list of moles for every element that's in the compound, use the lowest number of moles as a sort of a base for all of the ratios. You'll see more about what that means when we do an example. Once you've got ratios, and they're in whole numbers, you fill in the subscripts in the empirical formula. Let's try an example. Say you have a sample of a compound, and it's 1.472 grams hydrogen, 35.072 grams carbon, and 93.434 grams of oxygen. Our objective is to find out what is its empirical formula. Okay, here's our starting point. We have 1.472 grams of hydrogen, 35.072 grams of carbon, 93.434 grams of oxygen. Remember, step one is we want to change these all into moles. Well, here's how we can do that. We use the molar mass in this way. For hydrogen, we know that 1.008 grams per mole is the molar mass. So by dividing by molar mass, we're going to get moles. That turns out to be 1.460 moles of hydrogen. For carbon, we do the same thing, only the molar mass is different. Here we have 12.011 grams for every mole of carbon. When we do this problem, we get 2.9200 moles of carbon. For oxygen, well, the molar mass of oxygen is 15.999 grams per mole. And we do this, we get 5.8400 moles. Notice that I'm retaining all my significant figures. Sometimes that's important, so we're going to do it all the time. Now the next step, once I have my list of moles, will be to use the smallest number of moles as a sort of a base for my ratios. In other words, that's going to be the 1 in all these ratios. So I'm going to do this by dividing all of these by the smallest number of moles. So here's how I'm going to do this. The smallest number of moles is those of hydrogen. I have only 1.460 moles of hydrogen. Carbon and oxygen are larger. So I'm going to find the ratio of carbon to hydrogen in this compound, moles, by taking 2.9200 moles, that's carbon, and dividing by the moles of hydrogen, which is 1.460 moles. When I do that, I get a number that's really, really close to 2. It's within a few hundredths of 2. So I'm going to just round it off. Now I can also find the ratio of oxygen moles to hydrogen moles by taking oxygen's mole quantity, 5.8400 moles, and dividing it by that same smallest mole number, which was 1.460 moles of hydrogen. Here I get a number that's really, really close to 4. It's within a few hundredths of 4 again, and so I can round. All right, so what do I do with that? Well, I have a formula that's going to have a subscript for hydrogen, a subscript for carbon, and a subscript for oxygen. I've established that the subscript for hydrogen is going to be 1. When I found the ratio of carbon to hydrogen, I found that that was 2. When I found the ratio of oxygen to hydrogen, I found that that was 4. And so there's my empirical formula. Here's another one. Compound has 129.32 grams of sodium, 293.52 grams of chrome, and 313.98 grams of oxygen. And again, we're supposed to find its empirical formula. Okay, here's our starting point. For sodium, we have 129.32 grams. We want to change that into moles. So we look up the molar mass of sodium on the periodic table. We find out it's 22.99 grams per mole. So when we do this arithmetic, we find that there are 5.6472 moles of sodium in this sample. Do the same thing for chromium. Look up chromium on the periodic table. Its molar mass turns out to be 51.996 grams per mole. When we do this calculation, we get 5.6450 moles, pretty close to that of sodium, so there could be a 1-to-1 ratio there. Oxygen, same thing, only oxygen's molar mass is 15.999 grams per mole, and this will tell us how many moles of oxygen are present. The calculation shows 19.625 moles. Well, it's a pretty close call here, but the smallest number of moles is that found in chromium. So this is going to be our 1. We're going to assume this is a subscript 1 here. And we'll base our other ratios on that. So when I take 5.6472 and divide it by 5.6450, I will get a ratio of sodium to chromium. When I do this calculation, I find out that the number is, like I suspected, really, really close to 1. It's within a few hundredths of 1. The next thing to do is figure out what the oxygen-chromium ratio is. I want moles of oxygen divided by moles of chromium. So that's 19.625 moles divided by my 5.6450 moles of chromium. Here's what I get. I get 3.4765 when I do this to the correct number of sig figs. Now that's not very close to 3, so I can't really round down. And it's not very close to 4 either. To round to a whole number, I really need to be within a few hundredths of that whole number. So here's what I do. If I'm within a few hundredths of a whole number, I round to that whole number. In a case where, say, I had 5.999 or 5.997 even, I would round this to 6 because it's within a few hundredths. Or if I had 6.002 or 6.013 or something like that, both of those numbers I would round to 6. But if I've got a number like 3.472, that's not within a few hundredths of a whole number. So in that case, I look for a simple fraction. By simple fraction, I'm talking about things like 1/2, 1/4, 1/3, 3/4, 2/3, things like that. If I'm within a few hundredths of one of those, well, then I'm good. Now, you have to know what these are. Half, I think most everybody knows that's about 0.5. Quarter is 0.25. A third is 0.33. 3/4 is 0.75. 2/3 is 0.67, roughly. So look for things that are within hundredths of those decimals, and you will have some simple fractions you can rely on. Then, in these cases, when the ratios don't come out to whole numbers, you can multiply to end up with whole number ratios. Like, let's say, for example, that instead of being able to round to 2, I have to go to 1.5. So let's say this is carbon and this is hydrogen. My carbon to hydrogen ratio is 1.5 to 1. Well, I can't write a formula that says C1.5 H1 because this means atoms, and there's no such thing as a half of an atom. But here's what I can do. I can get lowest whole number ratios by multiplying both of these by 2. 1 times 2 is 2, that's a whole number, and 1.5 times 2 is 3, which is also a whole number. So that changes my ratio to C3H2. That's the lowest whole number ratio. So back to our problem here. If I'm at 3.4765, that's not close to a whole number, but it is pretty close to 3.5. So now what do I do with that? Well, if I could keep that half, my formula would have been Na1Cr1O 3.5, because that's what my ratios were. But I can't. So I'm going to double everything. And that'll leave me with Na2Cr2O7, because 7 is twice 3.5. Try this one. Okay, here's your answer. I've got calcium, 18.825 grams. I want to change that into moles. The molar mass of calcium is 40.08 grams per mole, which you can find in the periodic table. This tells us how many moles of calcium we have, and it's 0.4697 moles. I want to do the same thing for fluorine. Molar mass of fluorine is 18.998 grams per mole. So that will give me moles of fluorine, and the answer is 0.92999 moles. Now I want a ratio. I'm picking the smallest number of moles, which is the calcium number, and I now want to find the ratio of fluorine to calcium by taking 0.92999 moles and dividing it by 0.4697 moles. This ratio comes out really, really close to 2. And so that would bring me to the conclusion that there are 2 fluorines for every 1 calcium, and that must be my empirical formula. Try this one. Well, here I have a 0.245 gram sample, and it has only in it arsenic and oxygen. And it tells me that I have 0.192 grams of arsenic, and the rest is oxygen. So if I take my 0.245 grams and I subtract the amount of arsenic, 0.192 grams, the rest of it's got to be oxygen. When I do the arithmetic, I come up with 0.053 grams of oxygen. So here's my starting point. Well, I want to change both of these gram quantities into mole quantities. The molar mass of arsenic is 74.922 grams per mole. When I do this arithmetic, I find that I have 0.00256 moles of arsenic in my sample. I'll do the same calculation for oxygen. Oxygen is 15.999 grams per mole. When I divide 0.053 by 15.999, I get 0.0033 moles of oxygen. 0.00256 is the smaller of the 2 numbers, so I want to find a ratio of oxygen to arsenic by taking 0.00333 moles and dividing by 0.00256 moles. What I come up with is this, 1.289. Well, 1.289 is not close enough to a whole number to round it to either 1 or 2. So we got to look for a simple fraction. It's a few hundredths higher than 1 1/4, but it's pretty close to 1 1/3, actually. So here's what this is like saying. It's like saying arsenic 1, oxygen 1 1/3. Well, to get rid of the third, I'm going to multiply both subscripts by 3. So that leaves me with arsenic 3, oxygen 4/3 times 3, which is 4. So AS3O4 is my compound.